Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 31 in the series, where we continued the discussion of simplifying radical expressions. In particular, in this video, we're going to discuss how to simplify radical expressions involving addition and subtraction, as well as how to rationalize radical denominators. The main idea in adding and subtracting radicals is like terms, which, as we saw in previous videos, relates back to the original distributive property. In the exact same way and with the exact same proof that x plus 2x is 3x, the square root of 5 plus 2 square roots of 5 gives us, well, 3 square roots of 5. Now this works just fine and dandy as long as our radicals all have common radicands, arguments of the radical. But if they're different, like in this case there's a 2 and a 3 for our radicands, then, well, they in general don't simplify. There's really not a good way to simplify this expression, square root of 2 plus the square root of 3. That's really just where you'd have to leave it. Unless after simplifying, they turned out to really just be the same radical after all, with perhaps a different coefficient. Let's take for an example the square root of 75 minus the square root of 27. Now you might say right off the bat, well, these don't have the same radicand, we're out of luck. But let's first try to simplify everything that we can. We saw in the last video how to simplify radical expressions. Here's a nice little shortcut for when we're dealing with square roots. If I can see that there is a square in there, like in this case 25 is a part of 75, well, I can take the square root of both parts. 75 is 25 times 3, and so if I just take the square root of 25, I'll get 5 square roots of 3. And likewise, 27 is 9 times 3. 9 is a square, and the square root of 9 is 3. And this means that the square root of 27 simplifies to 3 square roots of 3. So actually, this difference could have been rewritten equivalently in terms of square roots of 3. And so if we do so, we get 5 square roots of 3 minus 3 square roots of 3, which is just 2 square roots of 3. That's really all there is to adding and subtracting radicals. You simplify, and if you get like radicands, you can simplify some more. Rationalizing the denominator is something else. It was a much more important problem back in the day before computers and calculators, but it's still going to be an important problem for us now. Let's first discuss why it was an important problem, because I think this is pretty interesting. As far as I can tell, it has to do with what would happen if we wanted to get something like, what is 1 divided by the square root of 2 as a decimal? Really, the question of any irreducible square root, what is your decimal, is sort of a loaded question. These square roots, like the square root of 2, are called irrational if they don't simplify to an integer or another fraction. If they give you a decimal, then they're going to give you a decimal which never repeats. There is no fraction, no ratio of whole numbers, I should say, which is equal to the square root of 2. Its decimal goes on forever and never develops a repeating pattern where you just copy, paste, copy, paste. This stands completely against how the rational numbers behave, where eventually for every rational number, it develops a repeating pattern. A repeating pattern where we are just copying and pasting a fixed cluster of numbers over and over and over again forever, like the way that 1/3 becomes 0.333333333. That's not how the square root of 2 do. The square root of 2 here, just approximately given, or rather, if I put the dots here, I mean it goes on forever, so I'll dare an equality. But it begins this way: 1.414213562, and so on. You could follow this number for thousands, millions, billions of decimal places, and you would never see a repeating pattern begin and continue indefinitely. Now, this is probably a little disconcerting because there are going to be some reasons for real applications why we might want the square root of 2. And here we're saying we're only ever going to get a finite approximation of the square root of 2. We'll never really understand it infinitely. Yes, that's the case. That is the case. If we ever need more decimal places for the square root of 2, we can get them, but we'll never get them all. In some sense, any real knowledge of the square root of 2 will always be wanting and imperfect. And yet, for something we can only ever approximately know in a concrete sense, the square root of 2 pops up quite a bit, especially in geometry. For example, it pops up whenever I have a right triangle, which is also isosceles. If the right triangle, for example, has two legs of length 1, the hypotenuse's length square root of 2 by the Pythagorean theorem. And if we want the similar triangle who's got a diagonal of 1 instead, dividing everything by the square root of 2 gives us this triangle. And so it's a geometrically meaningful question to say, well, what is 1 over the square root of 2? So back to the problem. How do we calculate 1 over the square root of 2? Oh, why, with a calculator, of course. I just go to my handy TI-84 and I type that on in and I get the following decimals. Okay, well, are there more? What's the relationship between the square root of 2 and 1? Everything kind of gets obscured when you just give it up to the calculator. And also, will you always have one? I mean, yeah, no, only when it counts? I don't think these are great questions. I think a very important idea in mathematics is that one of the things we're trying to do here is see the forest for the trees. And that doesn't happen if we export all of our thinking to the calculator. We miss very important interconnections. So what about with no calculator? What about how this was done historically? How would I do this division? And let's even say that I have some approximation of the square root of 2 first. We're going to need that if we're going to do any long division. But even if I take a bad approximation, like 1.41421, only 6 digits here, this is still going to be a real pain to do in long division. Let's see why. Because putting the 1 inside the house here, square root of 2 and its approximation right here, I would have to first move my decimal places and then say how many times does 141,421 go into 100,000? Well, no times. So moving down along the line, I put my decimal up, I add another 0. How many times does 141,421 go into 1 million? You could guess and check and find 7 eventually, but man, we're only on the second question here, and we gotta answer how many times does this big number go into this even bigger number? Yuck, gross, disgusting. Okay, I agree. That's not what I would want you to do. But that's the thing. Is there a trick? Is there a smarter way of doing this? And the answer is yes. The answer is yes. To see what this trick looks like, remember that 1 times anything is just itself, no matter how weird that 1 looks. So, for example, what if I took square root of 2 and multiplied by it on the top and bottom? Well, on the top, it's just 1 times itself. That's the square root of 2. On the bottom, that's the square root of 2 times the square root of 2, which is the square root of 2 squared. Now, a square root times itself cancels, because squaring cancels square roots. So we wind up with just a 2 on the bottom. Wait, that's it? That's the whole trick? Is that really any better? Is it better to divide the square root of 2 by 2 than to divide 1 by the square root of 2? Yeah, it's way better. That's kind of remarkable, right? Let's see why. If you take this time take as nice approximation as you want. Doesn't matter how many digits you use. Let's use all the ones that my calculator popped out with, right? Now, to set this up for long division, we put that long number in the house. We put the 2 out front. Look how much simpler this divisor is. So when I go to do my division, I can answer these questions quickly. How many times does it go into 1? None. How many times does it go into 14? 7. Bam! That quick. And then difference is 0. 0, drop the next one down. How many times does it go into 14? 7. Difference is 0, drop the 2 down. How many times does it go into 2? Once. You see how easy this is. So much easier than the last one. Now, because of this incredible reduction in difficulty, rationalizing the denominator used to be really, really important. If you were going to do any ratio that had an irrational number in the denominator, you needed to rationalize it first, or you were going to be there all day. So wait, why is it still important? If that was why it was important, why is it still important? It's still important for 2 reasons. Number 1, this way of simplifying the fraction that we just used is actually going to happen over and over again. There are a great number of tricks that are based on this idea about multiplying by a curious-looking version of 1, which simplifies our expression greatly, right? So it's a good idea to get used to that pattern. In fact, when you add fractions with unlike bases, that's precisely what you're doing. And number 2, it's a great lesson in and of itself. Like, it's a lesson that some problems that look hard when you start to tackle them straight on get way easier if you can just change the form a little bit. And sometimes that's just as easy as multiplying by 1, a curious looking version of 1, albeit. Now, that was a lot of long wind on my part, so let's look at an example that's a little bit cleaner. Rationalize this denominator. So we take the denominator, square root of 5x, and we multiply by that in the top and bottom. That looks like this. A square root times itself cancels to its argument, and we just get the radicand 5x on the bottom, and the square root of 5x is now multiplied by 3x on the top. Now the x's do cancel, but there's something to be concerned about here. Something over itself is 1 only if that x wasn't 0. So this last orange expression is only true if x wasn't 0. What this means is that if 0 is forbidden, you couldn't put 0 into this function at the beginning because it would have divided by 0, it's still forbidden at the end, even if it canceled. And we'll talk about that a lot more when we get into the last section of this course, which is on rational functions. But for right now, I'll just mention it does cancel. This is the right answer, but something has happened in order to do that. We've assumed that x wasn't 0, and that assumption is good. We're going to have to keep track of that. Okay, so now I'd like you to copy these critical notes. Prove to me that you watched this video. Adding and subtracting radicals is just like terms. If they have a like radicand, you can factor it out, and you just get the sum or difference of the coefficients. That's how you take a sum or difference of radicals. Now, rationalizing, you take the denominator and its square root, and you multiply on the top and bottom by it. That cancels the square root and just gives you our radicand b. And on the top, it persists, and we have a times radical b. That's it. So here are your praxis exercises for the day. Give these a shot. Pause the video. Okay, let's see how you did. To do number 1, we should simplify everything. Now, you could do this the way we did it in the last video, making factor trees and pulling out a certain number of factors. You know, this is a square root, so we're looking for pairs. But we could also, in the case of square roots, look for squares, which are pairs of factors, right? 25 is 5 times 5, 16 is 4 times 4, and so on. So if we see those, we could factor those out. The square root of 25 is 5, of 16 is 4, of 9 is 3, of 4 is 2, and look what's inside the radicals still. We have a square root of 5, we have a square root of 2, we have a square root of 5, we have a square root of 2. So these won't all combine. We can't mix the 5s and the 2s, but we can rearrange things a little here just to see it. Combine the square roots of 5 together. 5 minus 3 and 4 minus 2 are both 2. So we wind up with 2 square roots of 5 and 2 square roots of 2. That's pretty much it. I wouldn't take it any farther necessarily, but if you notice that there's a 2 common to both of those, you could factor that out, but this is probably your better answer here. Now, what about this guy? How do you rationalize this? Well, you take the denominator and you multiply on the top and bottom by it. On the bottom, that gets rid of your radical. The denominator is now rationalized. And on the top, we have 10 times radical 6x.
So once we do that, we will just basically have to reduce the 10 and the 6. They both divide by 2. That gives me a 5 on top and a 3 on the bottom. We keep the x right here. It doesn't cancel with anything this time. And that's the end. Okay, thank you for your patience. Good luck with your studies, and I will see you in the next video. Have a great day.